Hi everyone, in this session I am going to teach you about basics of digital circuit design. Since we are trying to teach everything from scratch, in this session I will give you the fundamentals of digital circuit design so that you can able to do some complex designs using hardware description language like Verilog in future sessions. So let's begin. So these are the contents of this session. First of all, I will give you a brief idea of logic gates and Boolean algebra, and then I will move to combinational circuits, then flip-flops, and finally I will conclude this session with sequential circuits. In this session, I don't want to teach just the theory, but I want to give you some real-world applications of these logic gates or combinational circuits also. So first of all, what is a logic gate? We all know logic gates are the basic building blocks of a digital computer. Let's say you have a computer. What is there inside that computer? It has different logic gates. These logic gates are used to manipulate the signals that are coming from outside. These signals are either analog or it can be digital, right? So these analog or digital signals are passed through a IOs where it will be converted into a digital values either 1 or 0. Once you got these binary values, you have to manipulate these signals so that you will achieve whatever function you want. So in order to manipulate these binary values, we need some circuits called logic gates. Let's take an example. If you have a input like this coming from two different inputs, and if you want to choose one of the input, you will require a logic circuit called multiplexer. With this logic circuit, you can able to choose which path you want to travel, either this path or this path. So this is one of the primary reasons we'll have logic gates inside our digital computers or any sort of integrated circuits. So here I have mentioned few logic gates like inverter or NOT gate, buffer, AND, OR, NAND, NOR, XOR and XNOR. We all know the purpose of inverter, right? Inverter will do the inversion of the signal. If there is a 1 here, the output will be 0. If there is a 0 here, the output will be 1. Similarly, the purpose of buffer is to pass the same signal. If the 1 is an input, then 1 will be the output. If 0 is the input, then 0 will be the output. So what is the purpose of this buffer? Why can't we just put a wire to pass 1 to 1? The purpose of buffer is to give some delay, and I will explain why delay is required in digital circuits in future slides. So inverter and buffer are clear. Now, what are these AND and OR gates? These are some basic building blocks of any digital circuits. This is an AND gate and this is a OR gate, right? AND, OR and inverter are called basic building blocks of any digital circuit. I will explain why they are called basic building blocks, and NAND and NOR are called universal blocks. Why they are called universal blocks, I will explain in next slide. And there are two other gates called exclusive OR and exclusive NOR. What are these purposes? We will see. So in this slide itself, I will explain what is the purpose of AND and OR and NAND and NOR. I think you are all familiar with the truth tables, symbols, all these things, right? So let me directly draw the truth table of AND, OR, NAND and NOR. So let's take two inputs X and Y and the output is Z. There are four possible combinations, right? If you have two inputs. So these are the four possible combinations. And if you want to have a AND gate, the output is A dot B. So 0.0 is 0, 0.1 is again 0, 1.0 is again 0, 1.1 is 1. So what is the purpose of this AND gate? Let's say you have a signal and you want to suppress that signal. So how to do that? You just connect the signal. This is the signal you have input and you want to suppress it to 0. So connect this signal with a ground or a 0 signal. Now see what will happen. If your input is either 0 or 1, no matter what the input is, it will always give you the output 0, because that is the purpose of AND gate. If one of the input is 0, the output is always 0. So in this case, you can use an AND gate as a suppressor. So this is the purpose of AND gate. Let's take NAND gate. What is the output of NAND gate? It is just inverted output of AND gate. If both are zeros, then output is 1. If 0 and 1, output is again 1. If 1 and 0, output is 1. If 1 and 1, output is 0. What is the purpose of NAND gate? NAND gate will give you AND plus inverted output. So this is why we call this gate as a universal gate, because it has a function of AND as well as inverter. Let's say you want to implement an inverter gate using a NAND gate. How do you do that? One way to do the inverter is either connect the other terminal, connect one of the terminal to input. Here the input is A, and connect the other terminal to VDD or binary 1. What happens if we connect the other terminal to 1? See, if one of the input is 1, then other input is directly opposite of the input, right? Here it is 0, so output is 1. Here it is 1, so output is 0. So by this way you can achieve inverter operation. There is one more way you can do the same thing. Just connect the same input to two inputs of the NAND gate. So what will happen? What is the equation of NAND gate? Y is equal to A dot B whole bar, right? What I did, I connected A and B together to A. So A dot A whole bar, which will give you A bar. This is what we want, right? We want a inverter using NAND gate. So we achieved it. That's why we call NAND as a universal gate. Even the same thing can be doable by NOR also. But you cannot do these things with AND and OR gates. So those gates are not in universal gates. Only NAND and NOR are universal gates. With these two gates, you can implement any logic function inside a computer. So these two are very essential gates. Let's see what is the purpose of XOR and XNOR gates. First of all, we'll draw the truth table of XOR and XNOR. Let's take two inputs A, B and an output Y for an XOR and XNOR. So the possible combinations are 0, 0, 0, 1, 1, 0, 1, 1. The output of XOR is if what is the equation of XOR? Y is equal to A bar B plus A B bar, right? So if both the inputs are 0, 0, the output is 0. If one of the input is 1, the output will be 1. And if both the inputs are 1, 1, output is 0. Similarly, the XNOR output is just inverted output of XOR. So 1, 0, 0 and 1, right? So you can clearly observe there is a pattern happening here. What is the purpose of XNOR? XOR, if there is odd number of ones, the output is 1, right? See, here there are no ones, so the number of ones here is 0. So output is 0. Here there is 1, 1, the output is 1. Here also there is 1, 1, the output is 1. Here there are 2 ones, the output is 0. So you can say, you can use XOR gate as a odd input detector. If there is odd number of ones, odd ones detector. And similarly, the output of XNOR will be turned on 1 when there is even number of ones, right? So XNOR gate you can use as a even ones detector. So that is the purpose of XOR and XNOR gates, right? So there are other applications also, like XOR gate can be used as a modulo 2 adder. What is modulo 2 adder? If you have two inputs A and B, and if you add them and divided by 2, and the remainder of this thing is called modulus, right? We know the operator of modulus. A mod B will give you the remainder. right? So here modulo 2 means a plus b divided by 2 and the remainder is the modulo 2. If you do that, a plus b, here 0 plus 0 divided by 2 is 0 and 0 plus 1 divided by 2 is 1, the remainder is 1, 1 plus 0 divided by 2 and the remainder will be 1 and 1 plus 1 will be 2 and divided by 2 has the remainder of 0. So you can use XOR as a modulo 2 adder. And what is the purpose of XOR gate? See, if you replace the 0 with minus 1, let's see what happens. A, B and XOR. Replace 0 with minus 1, minus 1, 1, 1, minus 1 and 1, 1. So the output of XOR will be minus 1 into minus 1 will be plus 1, minus 1 into 1 will be minus 1, 1 into minus 1 will be minus 1, 1 into 1 will be 1. So if you want to do a multiplication of these two numbers, you can simply represent by using an XOR gate, right? If you map 1 with plus 1 and 0 with minus 1, you can achieve the negative number multiplication by using XOR gate. I will explain what is the purpose of this negative number multiplication in future slide. This is very important because with a simple gate, you can able to do a multiplication operation. This is very crucial. The multiplication operation will take lot of gates, but you can do that using by simple XOR gate. So once we are familiar with logic gates, we will see what is Boolean algebra. So you have lot of gates, right? And inverter, AND gate, NAND gate, all these things. Instead of representing all the time with symbols, let's say we can represent those things with variables or you can say equations. In this particular case, I have showing the Boolean algebra function of f is equal to a plus b bar c. Sometimes I will write b bar as this or b tick. Both are same. So in this case, what does this represents? A plus b bar c. So it is a and b bar c. So this is, let's say, c and this is b bar. I am applying b here. I will get b bar here and I am adding that to a. So finally this is my output. So this is the logic diagram of this function f. Similarly, you can write the truth table for this a, b, c and how many combinations we will get for three different inputs from 0, 0, 0 to 1, 1, 1, right? 0, 0, 1, 0, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1 and 1, 1, 1. If you see, if you apply these inputs here, let's say 0, 0, 0. If this is 0, here 0 will appear. If b is 0, here 1 will appear and 1 into 0 is 0. So 0 plus 0 is f is equal to 0. If you do the same operation for all the combinations, the f output will look something like this: 0, 1, 0, 0, 1, 1, 1, 1. So this we will call truth table. So what is the purpose of this Boolean algebra? We'll see in next slide. So there are some basic identities of Boolean algebra. There are total 17 identities. You don't need to remember all these things. You can easily find these things. See, if you have x plus 0, what is the output? Adding 0 to anything will give you the same input, right? So output is x. It is as simple as that. You don't need to remember also. If you have x plus 1, if you add anything to 1, let's say x is either 0 or 1. If you add 0 plus 1, the output is 1. If you add 1 plus 1, the output is again 1 in case of Boolean numbers, right? It is like logic high plus logic high will give you logic high only, not two logic highs, right? So that is why 1 plus 1 is 1. Similarly, 1.1 or 0.1 will give you x, right? If x is 0.1, output is 0. If x is 1.1, output is 1. So you can say whatever value is there, if you multiply it 1, you will get the same value. Similarly, if you multiply the x with 0, you will get always 0. No matter what is the value of x, you will always get 0. Similarly, x plus x will give you not 2x but x. As I already explained, This is not a normal algebra. This is a Boolean algebra. And x dot x will give you x. X plus x bar will give you 1. See, why x plus x bar will give you 1? Let's say x is equal to 0. And if x is equal to 0, obviously the x bar will be 1, right? So 0 plus 1 will give you 1. Let's say my x is equal to 1, then x bar will be 0. So 1 plus 0 will be 1. So x plus x bar will always give you 1, no matter what is the value of x. Similarly, x into x bar will always give you 0. You apply the same logic. If x is equal to 0, then x bar will be 1. So obviously output is 0. If x is equal to 1, then x bar is equal to 0. So obviously your output is 0. So no matter what is the value of x, your output will always 0 for this kind of expression. Similarly, x plus y and is equal to y plus x, and x into y will be equal to y into x, and x plus y plus z will be equal to x plus y plus z, and x into y into z will be equal to xy into z. So you can even interchange these terms like this: z into x into y, or z into y into x. It doesn't matter, because this is a Boolean algebra. You can multiply the numbers in any order. Similarly, x into y plus z will be resulting into xy plus xz, and x plus y plus z will result into x plus y and x plus z. This is very important identity. We will come to this in next slide. And these two particular identities, 15 and 16, are called De Morgan's theorem. We will see what is De Morgan's theorem. And there is one very important identity, which is x bar of bar. I mean, if you do double bar like this, x bar of bar, this bar and this bar will get cancelled and you will get x. It is like complementing once and then again complementing once. This is exactly a function of buffer, right? Complementing twice will give you the same input. So once we are familiar with these basic identities, we will see how this uh, De Morgan's theorem will help you to solve some Boolean algebra functions. So first we will understand what is this De Morgan's theorem. If we have x plus y whole bar, then it will be equivalent to x bar dot y bar. Similarly, if we have x dot y whole bar, then it will be equivalent to x bar dot y bar. You don't need to remember this. Whenever you are in doubt, just draw the truth table and verify by yourself. That is the beauty of maths or science, right? You can verify at any time. So let's take an example x and y, and I want to verify whether this is equal to this or not. So I'm calling this as f1 and this as f2. So my f1 and f2, let's see whether they both are same or not. So what are the possible combinations? 0, 0, 0, 1, 1, 0 and 1, 1. Let's say if my x and y are 0, 0, if I do 0 plus 0, the output is 0, and if I do inverse of this, the output will be 1, right? Same thing. What happens if I have x and y are 0, 0, here x bar will be 1 dot y bar will be 1. So 1 into 1 will be 1. So first thing is clear, correct. Let's verify other three also. 0, 1 will give you here 0 plus 1 is 1, inverted is 0. 1, 0 will give you 1 plus 0 is 1, inverted is again 0. 1 into 1, inverted is 1 into 1 is 1, and again inverted is 0, right? Same thing we'll see for f2. 0 means it is 1, 1 means it is 0. If one of the thing is 0, so output is 0. 1 means this will be 0, so output is 0, and both are 1s means both will be zeros, so output will be again 0. So you can see the truth table verifies. So what I am trying to say is, if you have, you can see the function, right? This is a function of NOR gate, OR plus inverter, NOR gate. The NOR gate is equivalent to complement of AND gate. So to represent this, let's say 3 input NOR gate can be equivalent to 3 input complemented AND gate. This is very, very useful, because let's say you have a function like this and you don't have AND gates that are existing in your library. Then you can simply replace this function with NOR gate. That is the purpose of this De Morgan's theorem. Any function can be converted into NOR gate and NAND gate. So now we will see how this Boolean algebra will help you to simplify the circuits. Let's say my function is this a b c plus a b c bar plus a bar c. For this, in order to implement this function, how many gates I will require? To implement this function a b c, I will require a 3 input AND gate a b c, right? And to implement this a b c bar, I will require a 3 input AND gate with a inverter also, because C is available, we don't have C bar. So we need to convert it through inverter. C bar will come here and A and B will come here, right? And one more function I need to implement, A bar C. Since we have A, we need to convert it into A bar, and then we need to do multiplication with C, this C. So once we have these three individual dots A, B, C, A, B, C bar and A bar C, we need to do summation of these three things. We will do a XOR operation. So how many gates are required here? 1, 2, 3, 4, 5, 6. See, I will do this complete function instead of using 6 gates, just by using 4 gates. How? We will see. Take this expression again and we will try to simplify this. F is equal to ABC plus ABC bar plus A bar C. We'll see, we have already seen some basic identities, right? We'll use the same identities, nothing more than that. So let's take A common here from these two terms. Then what will happen? BC plus BC bar plus A bar C, right? And let's take B common from these two things. Then you will have B C plus C bar plus A bar C. So as we already know, C plus C bar will always result into 1. So this can be replaced with 1. And we already know multiplying 1 with any signal will give you the same signal. So this will convert into A dot B plus A bar C. Now let's see how many gates are required to implement this function. As you can see, this big expression is converted into small expression. Obviously, you will require small number of gates, right? Let's see how many gates are required to construct this expression AB plus A bar C. You will require a 2 input AND gate for AB, and you will require a NOT gate to convert A into A bar, and to multiply A bar and C you will require a AND gate, and to sum these two things you will require a OR gate. So I achieved the same function with just 4 gates. You think that you reduced only 2 gates, but think of in a very big circuits. If you can reduce a 2 gates, then it is a huge amount of optimization, right? So you achieved something very big by just doing a simple algebra simplification. Once you are familiar with these things, we will move to some advanced topic like combinational circuits. The combinational circuits are nothing but a connected arrangement of logic gates with a set of inputs and outputs. So what is there in combinational circuits? There is simple logic gates that are arranged in a fashion to give you the output that you desire. There is no memory element, so that's why these are called combinational circuits. If there is a memory element is there, then we'll call them as a sequential elements. We'll see that in future. So what is the purpose of the combinational gates? At any given time, the binary outputs are always depending on the binary inputs, but not on the state of the state of this combinational circuit. I will explain what is the state in future, but right now just understand this thing. Whenever there is a binary inputs are there, the binary outputs will always depends on these inputs and the logic function that you have implemented inside the combinational block. There are many examples of combinational blocks like multiplexer, demultiplexer, and decoder, encoder, and half adder, full adder. All these things are combinational circuits. But I will explain half adder and full adder in this session, and I will explain multiplexer, demultiplexer, decoder, and encoder when I will teach you Verilog. Okay, let's see what is a half adder. Whenever we are familiar with numbers, the first thing we can do with numbers is addition, right? So we'll see what is the Boolean addition. Let's take an example. If you have two numbers A and B, the A can be either 0 or 1, right? And B can also be either 0 or 1 in the case of Boolean. So A plus B will give me some output, let's say y. If I add these two numbers, A is equal to 0 and B is equal to 0, then output will be 0. If I add 0 plus 1, then again my output is 1. If I add 1 plus 0, the output is 1. But what happens if I add two ones? You cannot represent 2 in binary, right, with zeros and 1. What is the addition of 1 and 1? Ideally, I require 2. But you have only two symbols, 0 and 1. So how do I represent 2? I can represent 2 with 1 and 0. So I'll call this 1 as a carry and 0 as a sum. So if I want to design a circuit that can give me this kind of output, which we call as a half adder, right? So if you have two inputs A and B, and I want a function that can give me these two numbers, carry and sum of this A and B. In case of 0 and 0, there is no carry. So carry should be 0. In case of 0 and 1 also, there is no carry because the output is already represented by 1, which we want. In case of 1, 0, there is no carry, and only in the case of 1 and 1, there will be a carry. So let's draw the truth table of this function. I have two inputs, let's say here x and y, and I will have two outputs, one is carry and one is sum. So 0 0 will have carry of 0 and sum of 0, and 0 1 will have carry of 0 and sum of 1, and 1 0 will have carry of 0 and sum of 1, and 1 1 will have carry of 1 and sum of 0. So what is the circuit that is required to get this carry and sum? You can simply identify a pattern here for carry, right? If you remember, this thing is representing a AND gate, right? So 0.0 will give you 0, 0.1 will give you 0, and 1.0 will give you 0, and 1.1 will give you 1. So I simply take an AND gate, sorry, I simply take an AND gate and I will connect with my x and y so that I will get the carry. So carry is very simple, we got the carry. But how to get the sum? If you remember what gate this is? This is a XOR gate, right? So I can get the function of s by simply connecting x and y to a XOR gate. By this, I will get both sum and carry. So this circuit I call a half adder, right? So the expressions of s and c are like this. C is only 1 when both x and y are 1. So you can write c is equal to x dot y. Similarly, s is equal to 1 when in this condition, when x is equal to, when one of the input is bar dot other input is true value, plus in this condition one of the input is true value and other input is bar, sorry, this is dot bar, right? So this is the expression of carry and sum, and we already know what is the gate that is required to generate carry, it is a AND gate, and what is the gate that is required to generate sum, it is a XOR gate. Simple, right? With this two basic logic gates, we implemented a half adder. Very interesting. Let's see what is a full adder. In case of full adder, instead of two inputs, we'll have three inputs, x, y, and z. Since we have three inputs, how many possible combinations we'll get? 8 possible combinations from 0, 0, 0 to 1, 1, 1. So let's see what is the output. If you have all the three things are 0, if we add 0 plus 0 plus 0, output is 0 and there is no carry also. If we add 0, 0 and 1, then sum is 0 and there is no carry. Similarly, if you add 1, 1, 1, there is a sum of 1 and there is a carry of 1. So with this, can you able to find any pattern? It is not simple, right? So what we'll do, we'll try to find the expression for this thing. First, we'll try to find the expression of s. S is 1 when s is equal to 1 when x bar plus x bar, sorry, x bar, s is equal to 1 when x bar into y bar into z plus x is equal to when x bar y into z bar plus x into y bar into z bar plus x into y into z. You see there is a pattern here. What is the pattern here? The S is 1 whenever there is odd number of ones is present in inputs. In this case, the number of ones is 1, so S is 1. In this case, the number of ones is 1, so S is 1. In this case, the number of ones is 2. There are 2 ones here, so S is 0. Similarly, 1, 1, S is 1, 2 ones, S is 0, 2 ones, S is 0, 3 ones, S is 1. So, what is the gate that represents odd number of ones? S, that is an XOR gate. So, S can be obtained by 3 input XOR gate X, Y, Z. Simply we'll get S. But what is the function for C? Let's see what is the expression for C is. C is equal to 1 when X bar YZ plus X Y bar Z plus X Y Z bar plus X Y Z. It looks very complex, right? There is no pattern also. So in order to implement C, you will require 3 input AND gate, 3 input AND gate, 3 input AND gate, and 3 input AND gate, and then a 4 input OR gate. 1, 2, 3, 4 input OR gate, and there are complements also, so you require NOT gates also, right? So it is a very tedious job to implement this big function. So how to solve these big expressions or truth tables? We'll use a method called K-map method. In this method, we can able to solve any complex truth tables to a simple functions. Let's see what is a K-map. I think you are all familiar with K-map, but let's have one more time. We'll brush up these things. So since it is a 3 input thing, we'll have 8 blocks which is divided like this. One of the input is applied 0, 1, and other two inputs are here 0, 0, 0, 1. This should be 1, 1, right? Because it should follow the gray code convention. Because you can see the neighbors always have 1 bit difference. Here the difference is this, here the difference is this, and here the difference is this. By this way, you can reduce the function. So when x, y, z are 0, 0, 0, then output is 0. We don't need to draw zeros, we'll only see where the 1 lies. When x, y, z is 0, 1, 1, 0, 1, 1, here the C is 1, and 1, 0, 1, 1, 0, 1, here also C is 1, 1, 1, 0, 1, 1, 0, here also C is 1, and 1, 1, 1, here also C is 1. So how to combine these ones? There are multiple ways you can combine. Let's try one of the way. If you combine like this plus this plus this, what is the expression? C is equal to, if you combine these two things, the x is 1 and the y is complemented, so y is cancelled and you will get z plus, again the x is 1 and here the y is staying and z is complemented, so z is getting cancelled, plus this combination, the x is getting cancelled because it is complemented, so the expression is yz. See, this big expression is reduced into a very small expression. Now you will require only 2 input NAND gates of 3. You will get xz, xy, yz, and then sum this using a OR gate. That is how that is one way of achieving C, right? Yes. So we have simplified the C. But how to do the full adder using the two half adders, right? We have an expression for S which is a XOR of X, Y, and Z, and C we'll see what is the expression. I have restricted you to use only two half adders which is having one XOR gate, one AND gate, and one XOR gate, one AND gate. So how to do that? So again we'll solve for C. If you remember the K-map thing, it is like this: X, Y, Z, 0 1 0 0 0 1 1 1 and 1 0. C is 1 for these 4 things, right? So let's try one more possible way of combination. I want to combine these two things. I want to let these two things alone. So what is the expression for C? C is equal to this x into y bar z plus this 0 will be x bar into yz plus these two combination will result into x into y, right? So if you solve this C, you will get, take z as a common, then x y bar plus x bar y plus xy. Now if you see any pattern, yes, this is a XOR gate that is already available. Here you will get x XOR y, and here you will get x dot y. So that is already available. So you already have two inputs. Now all you need to connect with the third input, right? So I am taking this as my third input z. Let's see what happens. If I take this as z, so I want to achieve this function, right? This function of C. I want to achieve this C. So C should have z into x XOR y. So z is already available. The other input should be XOR of these two things. So I'll connect this to here. So this XOR and z will give me C is equal to z into x XOR y, right? One thing is clear. What about the other thing? We need to add it with xy, right? We already have xy. So let's take xy here and combine these two things with a OR gate. Then you will get complete C here, right? This is my C out. And how to get sum? It is already connected. If you see, x and y are XORed here, and that is XORed with z. So the output is x XOR y XOR z. So by this way, by using a two half adders and a OR gate, you can get a full adder. This is very interesting, right? We are not using any extra things. We are using simple logic gates, and we are achieving an addition function. Let's take a real world example. I have explained till now only two operations. One is AND or multiplication operation, and other thing is addition operation. What can we able to do with these two operations? You think these are very basic operations, but these are very crucial operations. You can implement anything with these two operations. If you have a AND operation or multiply operation, and if you have a addition operation, you can do a lot of cool things. Recently, you are hearing some terms like artificial intelligence, neural networks, machine learning, all these things, right? What they are trying to do? They are trying to mimic the human nature. What does we humans do? We'll take some inputs and we'll try to find some patterns and we'll try to identify something, right? Let's take an example of image recognition. If someone writes one like this, or someone likes one write this, or someone writes one like this, I can able to identify. But how can a computer can identify that all these three things are one? There you will require a neural network or artificial intelligence, so that the computer can learn this as all these things are one. Any neural network algorithm, if you see, they have a basic function called MAC operation. What does this do? MAC stands for multiply and accumulate. It will take some inputs and it will do the MAC operation and it will give some outputs. Based on this, it will learn the patterns. I am not going to explain how it is learning the patterns, but what I am trying to say is the neural network or artificial intelligence will require an operation called MAC, which is represented by using sum of dot products. If you have a dot product and you can able to do summation from, let's say, 1 to 100, then you can do the MAC operation in a by using a simple AND gate as well as OR gate, right? So if you can able to do AND plus OR, you can achieve anything that right now happening in this real world, like neural network algorithms, anything. In my personal experience, I have designed a MAC operation by using simple and OR gates, and I achieved the classification, or you can say neural network image recognition, and I achieved an accuracy of 98%, which is very high compared to the neural network algorithm accuracies. So by simply knowing what is the AND operation and addition operation, you can achieve MAC operation, which is a very essential part in these neural network applications, right? So once we are familiar with combination circuit, let's see what is a flip-flop. A flip-flop is a sequential circuit which is a memory element. It can store some data and it can give you the data whenever you ask it through a clock. Whenever you raise a clock, then it will give you the output. Whenever you don't raise the clock, it will store the data and it won't write any new data. That is the purpose of a flip-flop. It already exists, it already stores one data, and if you want to write anything into it, you just fire a clock and give the data and it will write into the flip-flop. We will see how what are the types of flip-flops and how they are working. So the definition of flip-flop is a storage element which is employed in a clocked sequential circuit, and it is a binary cell that is capable of storing one bit information, and it maintains its binary state until the next clock pulse. Until I will give you the next clock pulse, it won't give me the output. And there are various types of flip-flops like SR flip-flop, D flip-flop, JK flip-flop, T flip-flop. We'll see what are the different applications of these and how to realize these things. Let's start with SR flip-flop. SR flip-flop is called set, reset flip-flop. It has three inputs: set, reset, as well as clock, and it has two outputs: Q and QB. The QB is the complement of Q. Okay, so this is the symbol of SR flip-flop. You have S, R, and clock, and this is the characteristic table of SR flip-flop. So the purpose of SR flip-flop is like this: if you have both S and R are 0, the next state should be the present state. That means you should not change the state of this flip-flop state or the data that is storing inside the flip-flop. And when S is 0 and R is 1, R is 1 means I want to reset this flip-flop. So no matter what is the input, it should go to 0. So this is we will call as reset to 0. And if S is equal to 1 and R is equal to 0, no matter what is the input, it should go to 1. Then we will call this as a set to 1. And if S is equal to 1 and R is equal to 1, this is an indeterminate state, because you are trying to set and reset both at the same time, which cannot be happen. So this is the characteristic table of SR flip-flop. So let's see what is the characteristic equation of the SR flip-flop. Right? So as I already explained, if my clock is 0, then no matter what is the input of Q and S and R, my output should always stay in its own state. When the clock is 1, then only these things will affect my output, right? So if my clock is 1 and if my Q is 0 and S is 0 and R is 0, what I told, if both S and R are 0 and 0, it should stay in the same state. So it is staying in the same state. And if my S is 0 and R is 1, even though my X is 1, the output is 0, right? Similarly, you see here, if my S is 0 and R is 1, even though my previous state is 1, it is converted into 0, right? This is reset state, and similarly this is set state. If my S is 1 and R is 0, no matter what is the input, it will always set to 1. And if both S and R are 1 and 1, the output is indeterminate, right? So let's find out the equation for this by using K-map. So let's see the K-map of this thing. We have three inputs. I'm taking Q here and S and R here. So 0, 1, 0, 0, 0, 1, 1, 0, 1, 1 and 1, 0. See, you should not forget this. So the Q T plus 1 will be 1 when the combination is 0, 1, 0, 0, 1, 0 here. Then 0, 1, then 1, 0, 0, it will be 1, 1, 0, 0, it will be 1, and 1, 1, 0, 1, 1, 0, it will be 1. And there are two indeterminate states, right? Where it is 0, 1, 1, 0, 1, 1 here, and there is one more indeterminate state 1, 1, 1 here. So we will represent them by don't cares, right? So if you solve this K map, what you will get? You can club these four into one thing, and you can club these two things into one thing. So what will happen if you club these four things? The output qt plus 1 is equal to, here the q will get cancelled as well as the s will remain and r will get cancelled, plus if you do these two combined, then q will stay, and here the s will get cancelled and you will get r bar. So this is the characteristic equation of SR flip flop. So whenever you want to represent SR flip flop, you can represent by using this equation. Okay. Let's see what is a D flip flop. A D flip flop has two inputs. One input is data and other input is clock. We will call D flip flop as data flip flop. Why? Because the functionality of D flip flop is whatever the data is there, that will appear as next state. If the data is 1, that will go as 1. If the data is 0, that will go as 0. As simple as that, right? So what is the application of this D flip flop or any flip flop? You can say there are a lot of practical applications to these flip flops, like shift registers, counters, event detectors, data synchronizers, frequency dividers, delay lines, switch debouncers. All these are very useful applications in digital design, right? So we'll see one by one. What is a shift register? A shift register is a storage element that will give you the output whenever you fire some clock beat, right? There are multiple types of shift registers like PISO, SIPO, CISO, and parallel in serial out, serial in parallel out, serial in serial out, parallel in parallel out, PIPO, right? So in this particular case, this is a, we are giving inputs parallelly and we are expecting outputs parallelly, right? This is a PIPO, parallel in parallel out shift register. How does it works? It all the flip flops are connected through a single clock, and whenever I will write some data here and I fire a clock here, then in the next clock pulse, the data will appear here, right? So by this way, with three simple D flip flops, you build a 3-bit shift register, right? Why do we require shift registers? Let me tell you from my personal experience. While we are designing any chip, let's say chip in the sense application specific IC, while we are designing in any IC, first thing we are limited with area, right? You cannot have as much area as you want because the area will cost you millions of dollars. So first thing is area limitation. Once your area is limited, you are limited with number of pins also. You cannot have more number of pins because the size of pin of an ASIC is already fixed by the foundry. Once the size of the pin is fixed and the area is fixed, you will have definitely either 48 pins. Even the number of pins are also fixed. Like it will be in multiplying of Boolean numbers only. 16 pins, 32 pins, 48 pins, 128 pins, like this only. So you have to choose the pin configuration from these things. Let's say I choose a 48 pin ASIC, right? But I have a design which will require me, let's say, 500 pin input. Since I have limited by this, I cannot give 500 inputs from outside, right? This I faced the problem. So how to give 500 inputs to my design from a single pin? This is where the shift register will play. I can design a shift register of a 500 bit that will give me 500 outputs. Let's say these are 500 outputs, and there is only one pin I am using, serial in pin, and I am storing data sequentially in this, and I am getting the data output parallelly. So this is a serial in parallel shift register. You understand what I did here? Instead of giving 500 pins output from external world, I only used a single pin and I stored the data of these 500 outputs that I required to give to my design. Okay, let me draw one more time clearly. This is very interesting thing, right? I have a very big design inside my chip. Okay, I'll tell you what is the design also. It is a digital to analog converter, and I have a 500 digital inputs, and there are 100 analog outputs. I have a 100 5-bit DACs. DAC means digital to analog converter. So each DAC will have 5 inputs. So total 5 into 100, I have 500 inputs. But I cannot have 500 inputs from a ASIC, because as I already told, there is a limitation of number of pins that you can use. So what I did, I designed a shift register and I passed my 500 inputs through a single input using a serial in parallel out shift register. Once I input my 500 inputs into this serial in parallel out shift register, I will turn on a clock here and then I will get all my 500 outputs at the same time. Very interesting, right? This is how I solve the problem. Same thing you can do with any number of inputs, right? If you have 100-bit input, you can design 100-bit shift register. If you have 10-bit input, you can design 10-bit shift register. That will ease your designs, right? That is the purpose of shift register, and it is very easy. You just need to connect D flip flops in this fashion and apply the inputs serially to the D flip flop. This is a parallel in parallel out. If you want a serial in serial out, just connect this here. Then you have only one serial input pin, and the data is storing serially, and the output is coming serially. So this is a serial in serial out. If you take output here, then it is a serial in parallel. See, very simple. All you need to do is use the D flip flops and connect them accordingly to your purpose, right? This is one of the major advantage of using flip flops. So next thing is you can use the flip flops to design a counters. Why do we require counters? What is a counter actually? A counter is a circuit which can able to count the number of uh, times the clock has arrived. Let's say my clock is arrived 10 times, then my counter should give me an output of 10. Let's say my clock is arrived 5 times, then my counter should give me an output of 5. So how to design a counter? Simple, but again by using a D flip flops. Connect the D flip flops in this particular fashion, then you will get the counter operation. We'll see how.